I am head of sustainability and carbon reduction team at RINA. RINA is an Italian engineering consulting company with offices in 70 countries of the world, including India. And today I will have the pleasure of moderating this discussion on sustainable aviation fuels. As you know, aviation is responsible for approximately 3% of global CO2 emissions. Not much over the total, but it's one of the most hard to abate sectors. On one hand, so on the demand side. On the production side, you know, all oil and gas companies, all energy companies have impressive and challenging GHG emission reduction target. All of them want to be net zero by 2050, more or less. And since this includes scope 3 GHG emissions, so indirect emissions associated to the use of the products, it's very important to decarbonize also the products, the fuels that they are supplying. So, considering the importance of aviation in terms of GHG emission and the need to decarbonize fuels, it's really important to hear about sustainable aviation fuel production. So I will leave now the floor to Mr. Richard Matters. Please come to the stage. You're already on the stage. Who will deliver a presentation on accelerating aviation decarbonization, technical advancement in UOP, ESAF, and ETJ. Please, the floor is yours.
Good morning, everyone. I've been told as I'm tall and a little bit of noise, I may have to be bending down rather than standing up too straight just to recognize this. So I have the pleasure of being the first to present during this session. So what we're going to be focused on is, for the first 15 minutes, I'm going to provide an overview of Honeywell's UOP advancements in ESAF, so via the methanol route, and ethanol to jet technology offerings. So first, what I'd like to do is give you a broader perspective. And that's what this slide summarizes, which is the Honeywell UOP technology offerings for the production of renewable fuels. And I always say renewable fuels because we speak a lot about SAF and ESAF, but it's also the routes to renewable naphtha, renewable diesel, etc. But our focus is on ESAF and SAF. You'd heard earlier in the previous session on the HEFA route. Now, the HEFA route to SAF has been the predominant commercialized route over the last decade. The focus now shifts more towards those alternate feedstocks and alternate routes to renewable fuels. Hence why the focus of what we're discussing now is the technologies in the blue box. The e-fining technology, which is the Honeywell UOP trade name for our methanol to jet technology for the production of SAF or ESAF, depending on the methanol source, and separately also our ethanol to jet technology. So I'll start with our methanol to jet technology. And what I'm presenting here is a high-level overview of the building blocks. The feedstock is methanol, and you're going to hear a lot about the methanol technology in the next presentation from Madhan and Johnson Matthey. So I'll leave the discussions on methanol to him on that one. But our focus is on the commercialized building blocks to provide an overall route for that methanol to jet. One of the things I always say is I would describe the technologies here that we're speaking about as evolutionary, not revolutionary. So similar to how the HEFA process and the HEFA technology, which is in essence, it's an evolution of the hydroprocessing technology, the methanol to jet technology, which we launched in 2023, is an evolution of Honeywell UOP's methanol to olefins technology. So the first step transforms the methanol to olefins. The next step is the oligomerization. And then finally, hydrogenation, splitting those out into the separate building blocks. What we have done is we have taken those building blocks and we have optimized the overall process with a focus on CapEx and OpEx reduction, as well as yield and performance optimization. One simple example is that the MTO design, it's been simplified for the methanol conversion to a mixture of light olefins. So for example, we've been able to eliminate multiple pieces of equipment, reducing by about 30% in terms of the equipment cost, and reducing the utilities versus the traditional methanol to olefin process. So again, if I now step to the ethanol to jet process, you'll see a similar overview here of the steps to produce renewable fuels, but this time from ethanol. So while the final steps include oligomerization and hydrogenation, you'll note that the first step is dehydration. Again, our focus is on the evolution of Honeywell UOP long commercialized technologies. So you've probably heard me speak several times about technology evolution rather than revolution. And that's what this slide is all about. This provides an overview of the technologies or the building blocks that I've spoken about in the previous slides. So if I take from these as an example, methanol to olefins technology. So methanol to olefins technology is a simple example. There's already more than 45 years of combined commercial experience with units up to 2.4 million tons per annum of methanol feed. There's multiple examples of the commercialized oligomerization technology from Honeywell UOP, whether it be with the Cat Poly technology, INALC, or Cataline technologies, which are all listed here. Each of those have been specifically designed and optimized for their own purpose, and it's the same on the selective hydrogenation. So if we step back from just the building blocks, also looking at Honeywell UOP as a company, we've spent more than 50 years researching, developing, manufacturing, and optimizing catalysts for a full range of technologies right across the refining and petrochemical technologies. Now, whenever I speak about our process technologies, whether they be the older technologies or those that are announced in the newer evolutions of those technologies, we look at them and we present them in the same manner in terms of providing confidence to the end user. We provide guarantees in terms of process performance, catalyst life. We provide warranties on the intellectual property, on the engineering, on the equipment offerings. It doesn't matter how new technology is, we stand behind all of our technologies. In essence, I normally say every dollar that is spent, in this case I will say every rupee that is spent, we put at risk, whether it be in terms of the guarantees or the warranties, to give that security to the end user. So this slide now provides an overall awareness of the commercialization of the respective technologies to date, with focus specifically on ethanol to jet and methanol to jet. So we have 10 licenses for the methanol to jet, and we have 10 licenses on the ethanol to jet. Those that have been publicly announced are already noted below, and you can see the scale of some of these units. The fantastic thing is that I'm able to stand in front of you here today, and for those that will be aware, we were very pleased with the announcement yesterday by the Indian company Trualt Bioenergy, who are now a licensee of the Honeywell UOP ethanol to jet technology. So the great thing is, I'm able to say this presentation is already out of date, reflecting the most recent press announcement by Truolt Bioenergy. So I'll just move to an end summary now. So if I summarize in what we've spoken about, with both the ethanol and the methanol routes offering independent routes for the production of renewable fuels, we are building out our offerings for the alternate feedstocks versus HEFA. Both ethanol and methanol are available in significant quantities from a global market. This allows, for example, a hub and spoke project development, allowing for economies of scale and the strategic sourcing of the feedstock. Both technologies are based on Honeywell UOP technology, the building blocks with direct operational experience. All of this builds on our presence in India. So we've been present here for more than 80 years, and we've been a long-standing partner within the local refining and petrochemical industry. You'll maybe have noticed in one of my previous slides, if I step back, what I should have noted is that, for example, our ethanol to jet technology, the primary development location of that is India and the receipt of the Golden Peacock Award. So whenever we talk about India for India or indigenous offerings, our ethanol to jet in India truly is a local offering. Just stepping back to my summary slide, overall, I'm also pleased to say that not only was my last slide out of date, this slide is also out of date. For those that will have been aware, there was stepping onto the HEFA route with eco-fining. There was an announcement by Tata Projects on Tuesday at IEW with respect to Honeywell UOP, Tata Projects, and a company called SAF1 working together on the eco-fining, which is our HEFA route to sustainable aviation fuel. I appreciate this presentation is focused on ethanol to jet and methanol to jet, but I'm in India and I want to ensure the recognition of the local Indian companies working towards the production of sustainable aviation fuel. So if I just look to conclude, we have 20 licenses to date across the methanol to jet and ethanol to jet routes, including in India, and we're always eager to speak with those that are interested. So I'd just like to conclude by thanking you for your time. Whether or not, hopefully there may be time for questions and answers at the end of the session. If not, please feel free to approach me directly, or even better, please come across to the Honeywell booth or across in Hall 3, where myself or my colleagues will be able to answer any questions for you. So thank you very much for your time. Thank you.
Thank you. Thank you for that. Now we stay on a similar topic with Mr. Madhan Janardhanan, who will deliver a presentation on unlocking the fuel of the future, strategies for eSAF production with methanol. Please, the floor is yours. Thank you.
Thank you for the introduction, Chairman. My name is Madhan Janardhanan. I'm the Methanol Technology Manager. I look after all flavors of methanol with respect to catalyst and technology within Johnson Matthey. So today I'm going to speak about the strategies for eSAF production with e-methanol. Basically, how we can utilize the methods to produce e-methanol and how we can utilize that to produce eSAF. Before deep diving into the presentation, I would like to speak about the mandates increasing in the last year. Basically, EU has requested for 2% reduction in greenhouse emissions on the aviation industry, which is hard to abate. Now, and then UK followed, and in December last year, India has announced about the requirement for reducing the emissions in aviation industry. Currently, this market is served by HEFA. As we increase in the demand for aviation fuel, HEFA is not sufficient due to feedstock constraints. And EU and UK has been providing incentives for producing SAF from power to X sources. Hence, there is a future for e-methanol through MTJ to eSAF. And let's see how we can produce. Now, let's see the methanol to jet value chain. So methanol can be produced from sustainable sources through CO2 hydrogenation or waste gasification of municipal waste and biomass. And this can be processed in the methanol unit, and we can produce tradable methanol, which can be either used to produce eSAF through methanol to jet, or it can be sold in the market to fuel the shipping industry or to produce e-olefins. Now, I'm going to talk about first a bit on methanol technology, how we can produce methanol from CO2 hydrogenation, and then integration of methanol plant with SAF, that's through MTJ, and with two strategies. That's one is hub and spoke model, where feedstock is limited, and if feedstock is abundant, then we can have a large e-methanol plant to provide feedstock to a MTJ plant. Let me explain the methanol technology. So, principally, the methanol technology is no different from what we are being offering for last 60 years on fossil fuel industry. The major difference here for an e-methanol is we don't have carbon monoxide. The feedstock is carbon dioxide and hydrogen. So the challenges with the process is we will produce more water because every mole of carbon dioxide will produce a water as byproduct. So that will limit the reaction rate. The second thing is we need to know that the reaction is very lazy. The heat release is slow. So we need an active catalyst to support this. One is to move the reaction forward because of low reaction heat, and second one is the effect of water. Let's go and look at that detail in the next slides about the catalyst. Now I'll talk about the flow sheet. Basically, the flow sheet utilizes similar components what we have used in natural gas-based plants in the last 60 years. And JM scope will be compression of feedstock, purification. The CO2 has a lot of impurities which needs purification, followed by methanol synthesis loop. I'll talk about the reactor and the loop arrangement in the next slides, and distillation. So with this flow sheet arrangement, we can produce any grade of methanol which is marketable currently, marketable based on the standards available in the market. AA grade or IMCA or any marine grade which comes in the future. And it also, the grades required for methanol to jet is lenient than the commercially traded grades. Now let's look into the reactor. As I said earlier, the reaction is lazy, so we need an active catalyst, and also we need more catalysts. So we need a converter which can handle more catalyst volume. The second thing we need to note here is we are also having the heat release is smaller, so we don't need a lot of heat transfer area. Hence, we have repurposed the reactor which has been invented several years back for natural gas reforming, based on natural gas reforming plants, where the catalyst is on shell side. The reactor is basically a shell and tube exchanger without a tube sheet in one side. So gas goes through the tube side and comes out on the shell side, and catalyst on the shell side. So this gives high catalyst volumes per converter volume, and we don't need steam system because the reaction is lazy. With this gas-cooled arrangement, we can control the reaction temperature within the envelope, and it is low cost and highly reliable because we don't have pressure parts inside this reactor. And we also don't have thermal expansion issues because there are not any fixed tube sheets inside the reactor. And the next thing we have managed to do is like avoid a steam system. These plants are relatively small capacities at the moment. Having a steam system does not come without any additional costs. So we have looked at how we can reduce the capex and opex. Hence, we have integrated the process heat release to distillation to maximize the heat recovery from process to distillation to drive the reboilers, and we top up with electrical reboilers or a heating medium, which could be hot oil or any organic fluid, which can act as a heat transfer vector. And then one of the things we need to understand is like the feedstock is very expensive because of the electrolysis. Power generation is renewable, then electrolysis are expensive. So feedstock efficiency is very important. Hence, we need a high circulation loop to serve this requirement. So we have ended up with this tube-cooled reactor, which is low risk, which is already proven, and 15 reactors are already in operation, 2 in CO2 to methanol application. We call this technology Emerald. Let's talk about the catalyst. So as I said earlier, reaction is lazy, so we need an active catalyst. So it's basically a copper zinc catalyst. This is the 17th generation catalyst we have developed for this purpose with silica dopant. Means that the catalyst will have same beginning of life activity as the previous generation, but it will have 30 to 50% higher activity based on the purpose during end of life. So in clear terms, we can say that the catalyst volume are less than 30% when compared to the previous generation for the same purpose, any purpose which is applicable. So here it helps us to reduce the reactor size because of the increased catalyst activity or longer run length as well. We normally size the catalyst bed for 4 years. In that terms, we have a 30% reduction in catalyst volume, giving the same lifetime. And silica dopant also helps in providing a hydrothermal stability against sintering. That's a big issue when you have CO2 hydrogenation, because every mole of methanol produced will produce a mole of water. Hence, a highly active catalyst is important. And we have a robust manufacturing and supply chain process, so ensuring catalyst supply for the lifetime of the plant. And we also have ongoing R&D development for catalyst and technology development, which will ensure that the clients are up to date with the technology for the future. Here, we can see a number of boxes. Basically, it's a distribution of capex. When you look at the large box, that's the production capex and opex cost for the hydrogen. And then the next large one is the CO2 production. So feedstock efficiency is very important. And more than 50% of the cost of methanol is because of hydrogen production costs. An efficient loop can help you to reduce the levelized cost of methanol. And what we have achieved is, with our Emerald loop, is 8% reduction in OPEX, that is contributing to a levelized cost of 7.6%. Now, let's talk about the MTJ. In November 2024, Johnson Matthey and Honeywell UOP announced partnership on methanol to jet for production of eSAF. And as Richard mentioned, both the technologies are built based on the proven concepts. There is nothing new here. Even the catalyst, what we are talking about, is already proven, and it is operating in natural gas services where we have CO2 injection, which is close to operating conditions of an e-methanol plant. The reactor is proven, the flow sheet is proven, it's just the application is different. And it applies to UOP Honeywell technologies as well. So we have a number of projects announced, and due to the time constraints, I will not go to every project. But what I would like to say is, like, there is 2 small plants operating already, one in Iceland, one in Chile, and one plant under construction. That's 100,000 kilotons per annum in China, and it is expected to commission in 2027. That's based on this flow sheet concept. Now, let's talk about the e-methanol, e-SAF production through e-methanol. So there are two options we can produce e-SAF from e-methanol. That's one is hub and spoke model. If the feedstock is constrained, that's the CO2 availability is less, and then cheap renewable power is not available in large quantities, then we can have multiple small e-methanol plants feeding to an MTJ plant which can produce an industrial scale. So methanol is easily tradable, and it is also available in the market and transportable as well. So having a hub and spoke model, if the feedstock is constrained, ensures a single MTJ plant which can get methanol supplied from variable sources. The other model is having a larger e-methanol plant serving the methanol requirement for an MTJ plant. As you know, this MTJ plant also produces some byproducts which can be recycled back to the methanol plant. That's hydrogen and carbon, which are very expensive feedstocks. By combining these two plants together, we can get benefits on improving the levelized cost of eSAF. That is basically combined utility savings, hydrogen and carbon efficiencies, and interface optimization. And this unlocks additional value. Roughly, it translates to 3 to 4% of increased eSAF yield. For a 240,000 kiloton plant, we are getting roughly 6 kilotons per annum in addition, which translates to a total revenue of about $16 million per year. With this, I would like to say the renewable methanol projects can treat multiple fuel markets. So with hub and spoke model, you can sell the e-methanol either to MTJ plants or sell the methanol to marine or other applications. And MTO purity requirements are lower than pipeline spec or tradable spec. So if on an integrated plant, we don't have to refine the methanol to tradable qualities. In that way, we can reduce the utility costs. And by going with Honeywell UOP and JM, both technologies are mature, has been applied in fossil fuel technologies, and it's repurposed for this application. Hence, the technology is bankable and risk is lower. And as Richard mentioned, we are going to stand behind the client for the success of this technology and operation of these plants, not just up to the commissioning. We will work towards by supporting throughout the lifetime through our technical services. And based on the availability of methanol, we can go either with hub and spoke or a single large methanol plant serving an MTJ unit. Thank you. And based on the time constraint, I cannot tell more. If you want to speak with us, please visit us on the booth in hall number 3. Thank you.
Thank you. Thanks a lot, Madhan. Next presentation, that will be by Sudarshan Kumar Singh, and will focus on economics in sustainable aviation fuel through CO2 capture. Please, the floor is yours. Thank you.
Good afternoon, everyone. Myself, Sudarshan Singh. Currently, I am working in NTPC as a senior manager looking after decarbonization, specifically in R&D center of NTPC. So the journey begins with the decarbonization journey begins with the India's vision to achieve net zero by 2070. As already government of India mandate is there to achieve that net zero. So in line with that, NTPC being a thermal power producing station, we have a mandate to reduce our emissions and as well as to venture into renewables and other energy sectors which are low in low carbon intensity, as well as which are basically reducing the emissions. In line with that, Netra, which is R&D wing of NTPC, has taken up initiation with carbon capture and utilization, where we are basically producing different kind of products by using captured CO2. In line with that, which basically meets our focus, or I would say goal, which enables India's energy security as well as food security. When it comes with the energy security, we have like liquid fuels, gaseous fuels, diesel, petrols, gasoline, methane, LNG, and whereas in terms of food security, it comes with the fertilizers. So in liquid fuel, we have already commissioned one 10 TPD, where it's a small demo project, that is 10 TPD CO2 to methanol, and one is upcoming ongoing ethanol project is also ongoing. So these two has already met our I would say liquid fuel strategy. However, we are also upcoming with 150 TPD of CO2 to urea as a pilot project at Pudimatka, which is going to be India's green hydrogen hub in coming years, where NTPC is coming with a mega scale power, I would say chemical projects which will be derived from CO2 and hydrogen. So in this particular context, SAF, we touched SAF through ethanol. Since we have already commissioned methanol, but SAF, we touched SAF through ethanol. So now I would like to tell how the journey proceed with the SAF. So everyone knows what is SAF, basically sustainable aviation fuels. The global market already it is current global market is 238 billion, projected to grow by CAGR of 8.2. European Union has a mandate to for sustainable aviation fuel. India also has a mandate. So seeing the market and seeing the energy transition or shifting towards from conventional route to sustainable route, we also thought that we will be also putting our some diversification in this particular sector. So everyone knows the conventional process, sustainable process. So we chose basically power to liquid, which will be generating SAF through CO2 capture. And once we capture the CO2, then we'll be using hydrogen and we'll be producing ethanol. There are multiple routes. We can produce methanol also and ethanol also. So there is a route of methanol to SAF, and there is another route to ethanol to SAF. We chose ethanol to SAF. Currently, the project, the upcoming project is very small, which is 1800 TPA, which is almost 5.6 TPD. That is demo plant, where we will be using 25 TPD of CO2 captured from NTPC Simadhi thermal power plant, and we'll be using 2 TPD of green hydrogen. And after making ethanol from this two particular feed, we will be producing SAF through conventional route, ethanol to ethylene to oligomerization, dimerization, and then I would say after hydrogenation of that olefins, and thereafter producing to SAF. So in CO2 capture, how we proceed with this particular technology in CO2 capture, that in post combustion we have a lot of sulfur. So after desulfurization unit, we since the purity of CO2 is very important in synthesis of other derived chemical like methanol or ethanol. So we chose basically chemical route, where modified amine was taken, and where we basically based using modified amine, we captured the CO2 after FGD. Earlier we did project with physical route, also biological route, but as per our requirement and as per the need, we chose chemical route being a more efficient and more, I would say, matured with respect to green hydrogen, because since hydrogen will be used in this particular process, so ultimately hydrogen is going to be produced by electrolysis. But the water, since India is being a scarcity in water, so either it is terrestrial water or a coastal water. So we developed a lot of technology with respect to water, like flue gas based sea water desalination, or solar thermal based sea water desalination, or non-thermal forward osmosis based technology based water generation, and EDR based water generation. So ultimately, we are going to use all type of water, whether it is STP, sewage treated water, or coastal sea water, or any type of form of water. We'll be purifying it and making it water at a quality which can be feed to produce hydrogen. Once I get a CO2 of a required purity and hydrogen of the required purity, I'll be using that CO2 and hydrogen into reverse vertical shift reactor, where we'll be basically in a loop cycle. We'll be making syngas, and the syngas will be fed into the bioreactor, where the biocatalyst will be there, and they will be producing the ethanol. Though at present it is very challenging. This particular project is very challenging, but we are hopeful that with our licensor, since they have already did project in China and all, so we are hoping that the ethanol will be getting the ethanol. Once we get this ethanol, this ethanol will be fed will be used as a feed to produce SAF. SAF will be produced through ethanol to ethylene. Then ethylene will be compressed, and dimerization and oligomerization will take place, and hydrogen of the paraffin, and then the fractional distillation of the product, and which will be basically converting producing the SAF or diesel or requirement. So coming to the economics part, since we have already envisaged this 1800 TPA of SAF, so the costs which is coming as of now, with many assumptions, but the broader cost which is coming around, this is almost 320 rupees per kg, which is corresponds to $3.8 USD dollar per kg, where the capex is $1.43 USD dollar, and OPEX is 200.35 rupees per kg, and it corresponds to 2.38 USD dollar. It shows that it's the OPEX is basically, since hydrogen is being used into the pictures, where this OPEX plays a very important role. So by this presentation, I would like to mention that from CO2 to hydrogen to ethanol to SAF, the energy intensive is almost 37 kilowatt per kg of SAF. So the cost of electricity plays a very, very phenomenal role. So with different kind of I would say electricity cost that can be reduced, I would not say at a very from 320 to almost, I would it is coming somewhere to 259 rupees per kg with almost electricity cost of 4.5. My point is that if we are able to integrate the renewable power and I would say solar thermal or desalination based, where we can use the waste energy in terms of water purification or heat integration. So there we have an opportunity to reduce the cost of SAF to almost $2.50 or to $2. This what which it looks, because at 1800 TPA we are achieving at roughly 3.8 USD dollar. So that it has a very much margin where we can reduce with proper heat integration or proper, I would say, supply chain development. this can be reduced to almost $2.5. So key innovation which we basically gained, or we will be gaining, that will be basically putting our foot into brownfield compatibility of CO2 valorization, modular and load flexible of CO2 capture, flexible operation of our power plants when the load, when the RE power load is there, then we'll be using that power to basically produce our SAF or hydrogen. Summary is that CO2 to SAF is technically feasible and scalable. CO2 to ethanol to jet pathway is well suited for India. Energy demand dominates economics. Competitive SAF cost achieved with integration. Thermal power plant can evolve into low carbon fuel hubs. And in this context, the policy requirement is there because we don't have any particular pathways to determine the cost of this particular route. We have a pathways from DAC to ethanol, DAC to SAF. We have a pathways from HEFA to SAF, but we don't have pathway from CO2 capture from thermal power plant. There is a pathway from the waste gas, but not a pathway from CO2 capture power plant to ethanol to SAF. So we will be requiring certifications and other things as a challenging for this particular route. In the end, I would like to only say that these are very small steps, but there are multiple scalable projects which are coming at NTPC Pudimatka hub, and I would like to invite all the technology licensor and partners to collaborate with us for this particular hub. It will be huge, basically first in India. So thank you very much.
Thank you very much, Sudarshan. And now we can move to the last presentation by Kumar Saurabh, who will will present pathways for sustainable aviation fuel deployment in Asia. Thank you.
Mr. Chair, my fellow speakers, industry friends and colleagues, good afternoon. Also, I would like to thank the IEW and Technical Committee for this opportunity, for sharing this insight, the work that we do around SAF with various partner governments and all. Fortunately, I happen to be closer to the place where action is there in the South Asia. I am based in DNV office, Singapore, and Singapore, we have the largest active production capacity for SAF. So I will take you through the technology pathways. Then we will discuss about the availability of SAF, the feedstock, maybe on some parameters on the cost and the policy interventions that we can do to increase the adoption of SAF, particularly in Southeast Asia. This study or this insight that I would be sharing is mainly based on the clients and governments that we have been working on the Southeast Asia and within the region. So these are the various pathways. I believe the audience here is very much aware. For this presentation and all, because of the commercial viability and all, we would be focusing on the HEFA, FTA and ATJ, because these are the ones that we see because of the cost component and availability. These are the most probable pathways for the supply in the near future. A bit of on the SAF classification again. Various feedstock. We all recognize the complexity around SAF. There are a lot of feedstocks. There is a interplay of different production pathways and the scalability. All these three adds very much complexity to SAF, and based on that, there can be a broadly three classification where you see the bio-SAF, which is something which is coming from the organic feedstock. Then you have power to liquid, which is mainly not dependent upon the organic feedstock, and that is coming from the mostly from the renewable energy. And then we have a hybrid bio-SAF, which is combination of feedstock and the hydrogen base, which increases the yield of per se SAF. The most important thing to consider when we say about the pathways for adoption or deployment in Asia is to consider the technical maturity and carbon emissions. There are certain pathways which are better placed in terms of cost, but when we see the carbon emissions, they don't land up very competitive to other partners. So the technical maturity and the carbon emissions are very much important factor that needs to be taken care of by all the partners while taking up deciding the pathways for each of their countries or market that we see that they should be following. There are other kind of point of views like the standardization, the CORSIA framework and all that has to be taken into mind to devise a plan for the deployment. We see that FI again, it has kind of a very high maturity compared to others. The power to liquid very low. We don't have many benchmarks or projects to rely on the exact numbers. And also based on that, the adoption or when this technology pathways would be ready for real terms is kind of different. We know HEFI is kind of operational or competitive or being adopted now, and we similarly the FT and PTL we see that will come later towards 2040 and 2045. Yeah, coming to SAF availability. So for this study and all, we try to look into the availability for two particular anchor years, 2030 and 2050. Why so? Because the pathways that we have, the trajectory they are following, it will change. The current, the active and planned projects that are based on mainly on HEFA, and there is a limitation on the feedstock. So at some point of time, these feedstock are going to get exhausted, and that would be the kind of a limiting factor. But that will happen later towards the 2050. The current for 2030, the active and plant plants, they would be working operating on HEFA, and the supply would be sufficient. The limiting factors would be the policy interventions and the support that these governments are taking into consideration. For 2050, again, the feedstocks will become constrained, and we will have to kind of move to other pathways, mainly to the e-fuels. Also, the renewable fuels production, that is a very important factor. What you see here is that, again, based on when we progress, most of these production pathways for the other two fuel categories that I mentioned, renewable energy is an important factor. So, currently, the production, the potentials that are driven by the availability of feedstocks, they will move towards the availability of renewable energy. Both the e-fuels, those are mainly very much kind of land intensive and energy intensive. So the production and all those will move towards that. On the right hand side that you see the production yields, that shows. So all these pathways they have a kind of they can be optimized for the SAF production. For aviation sector, they are a bit of a constraint because they have to depend upon this liquid alternative and SAF. They have to compete with maritime and all. Fortunately, maritime and other sectors, they have other alternatives to kind of decarbonize, ammonia and hydrogen and everything. But for the aviation, primarily they have to depend upon SAF. So it will very much depend the incentives that governments and players are giving to SAF, so that all these production pathways, they can be aligned towards more production of SAF. So you see that the yield that we have mentioned, that when the processes are kind of for say maximum SAF, and when they are kind of as usual or default, which is the natural process, there is a kind of quite a difference between the production yields. Now coming to SAF production capacity, mainly for this we have looked into kind of 2030 for by technology and by country. So obviously by technology, when we see, we are very much aware that HEFI is the kind of leading both in kind of active and planned. The next candidate is ATJ. So that is again the planned capacity is much less, but on technologies wise, these two are the front runners when we say for 2030. By country, again what we see is the current active plant capacity. Singapore is the leading, but soon, very soon, China will take over. There are other countries like Malaysia and Indonesia. Those are also competing. They have a lot of plant projects, and very soon they would be competing or taking over. But yes, we don't see much of a change going further beyond 2030. Also, there will be moderate change into the dynamics. But yeah, a lot of this announced project, they have not declared that which pathway they would be taking. So there is a lot of uncertainty on that front. But yes, it more or less the dynamics that remains now, that China being the leading, that will remain same for towards 2045 and 2050 as well. Now feedstock potential in the APAC. So we have all the different feedstocks, and there is a probable pathway that this feedstock will go. So aligning both what we did in our techno-economic assessment, we aligned both the availability of this feedstock for the countries and the probable pathways that they are likely to go, and we have come up with the potential in the APAC. So what we see by technology on the left side, we have the potential based on HEPA, FTA, and ATJ, and on right hand side again by country level. And this is a kind of based on certain assumptions, the yield factors and the pathways that they are expected to take. Yeah. So the other important factor with Southeast Asia is the given that we have very less mandates and all. This region has the potential or to provide to the global market. So they are expected to be surplus on SAF production given the demand. One of the big uncertainty here is obviously China. We are not very sure that how much of the production of SAF China there will be surplus from China based on their domestic demand. But as a region, what we see given the mandates, availability of feedstock till 2030, there would be surplus in the Southeast Asian region to supply to the global markets. That's a key takeaway for the from the region. Also, I think this was discussed in the session earlier as well. For the current part, given the HEPA, the feedstock cost that is very important. Nearly 70, when we consider it right now, the 70% of cost is on the feedstock. So that optimization or that sensitivity is very much. We have seen in past, considering the HEPA, the feedstock prices or the SAF prices have fluctuated a lot, and that is the dynamics or that we have to deal with. So gradually, when we move to other pathways and there is more certainty, this sensitivity or this reliance or this variation, volatility will decrease. So coming to techno-economic assessment, we have considered all these 5 pathways for our assessment. So these are the 3, in these 3 graphs you will see that the current cost, future SAF cost and future eSAF cost, these are compared against the baseline jet fluid cost, which is around $0.7 per liter. And then you see that the e-fuels and all, e-fuels at currently are say 10x or 10 times pricier than the baseline jet fuel. Also, the SAF currently from the HEPA, they more or less they are twice the cost of the current jet fuels that we are seeing right now. But based on the cost reduction curves and all, learning curves and all, those are expected to go down. But this is most likely the scenario, and these are based on the assumptions that we have taken for the projects and benchmarks for 2025. Coming to MET, the marginal abatement cost, again, these are in case for HEPA, it is around 301 tons, followed by FT and then ATJ, and these are very important when you are required to choose the pathway that you would like to take for your market or the government bringing their mandates. Last but not the least, the policy levers. These are very important. So as I mentioned earlier, that SAF, particularly for aviation, is a very complex balancing between market forces, availability and all. So policy levers are the low-hanging fruits that must be adopted so that we can push, or the more and more SAF production is kind of aligned, or that can be diverted to the aviation sectors. And it has to be mix of what in our understanding is it has to be mixed of a levy and capex support, because the blending infrastructure and all, if we don't provide capex support, what we heard from the partners, they are not very keen to invest in that. So for that category, or that capex for the setting up the blending facilities and all, I think governments will have to provide the capex, and that can be funded by the fuel levy that we can impose. So the policy levers, combination of levy, capex, and opex support, it is not just the one that it can be just a fuel levy, but what we see and what we recommend is that it has to be a kind of a combination of all these policy levers. Thank you.
Thank you very much, Kumar, for your presentation. It was interesting to close this round of presentation with such an interesting review of the available technologies, their costs, the policy levers, etc. So thanks for this. Now we have a few minutes for a Q&A. If any of you have any question for our speakers, please feel free to raise your hand. Yes, please say your name and affiliation if possible to start. Thank you.
Hello. So even this is sustainable aviation fuel. So after the combustion, byproduct will be CO2 itself, correct?
This Richard,
I mean, after the combustion, it will produce CO2 itself.
Yes, that's right.
Yeah.
So again, we are making the fuel from the CO2. Then again, we are producing CO2.
Yes, that's why we are using biogenic CO2 or CO2 captured from hard turbine sectors.
But we are, I mean, whatever the CO2 is produced, we are not going to capture again.
No.
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 Hi, my name is Varun. I'm from Hyderabad, Telangana. So this is for Honeywell UOP. Where do we stand in terms of the certification? Like, is the technology ready? Can that be implemented, or can that be readily commercialized and supplied to any airlines? Where do we stand with the technology readiness?
So, sorry, just to get, was the question on the certification of the ASTM status for the methanol to jet, or was it a different question on certification? Sorry, just for my own clarification.
Yeah, that was for methanol to jet. So are we ready for the actual commercialization of the technology that has been developed?
In essence, yes, from a commercialization perspective, but if we differentiate on 2 points, obviously what I did in my presentation was to focus on the technology building blocks to demonstrate that the technology route itself is commercially proven and built up of commercialized technologies, evolution rather than revolution. But you raise a good point around the ASTM certification. Now that is something that we've been working through. It's quite a standardized and robust process. It's not a certified route as yet. However, I think it's passed the penultimate JET subcommittee and is up for considered approval, I believe, at the ASTM meeting in February. We believe, in terms of a timeline, that the approval will be in Q2, so sometime between April, June time on that. So the certification will be, we're expecting that this year. So that will all come together. But in theory, if you look at commercialization, moving from the basic engineering design phase through to the actual startup can be a typical maybe 3 years, 5 years, etc. on that. So that's why some of the companies are already starting down that route of looking at the licensing, the basic engineering design in advance of the ASTM. But certainly, I'm happy to go into more details of exactly the point on that one. But we're expecting the approval in Q2 for the methanol to jet process, as that's just a change to the annex of the existing alcohol to jet.
All right, thank you.
Any other question from the audience? Yes.
Yeah, this is a general question. Which refinery in India aggressively taking up of this manufacturing of SAF? Which refinery with respect to quantity?
Sorry, just on quantities?
Quantity, for example, now maybe any refinery having 10 million metric ton of capacity, they may be making around 0.5 million metric ton of ATF, for example. Which refinery in India is trying to make more SAF as on?
Yeah, and whenever you're looking at refineries, typically the starting point tends to be co-processing to produce SAF rather than maybe a full conversion on that. So obviously we can only speak about the ones that have been publicly released, but I would say the majority of Indian refiners are already focused on the production of SAF, predominantly in